Hi folks, this is part 2 of the Big Amp wrap-up, and this is a short video, but it includes some technical details I neglected in the first one about the power supply and the grid input, which I think has a lot of interest, and I will show that right now. Thanks for watching. The power supply. Here it is. So start in the middle here. This is the original Gates, beautifully made high voltage power supply or transformer, and it came with a little snubber across the outputs. A nice thing to reduce high-end noise. I've maintained the 2 diode strings that were in this thing. They're do-it-yourself 3 amp diode strings. They seem fine. The board they were mounted on was a bit low dielectric, so I improved that. But they seem to work fine, but I do have some alternate diodes to put in there if I need them. I have to stop for a second here. Okay, we're back here and recording, I hope. And yeah, where was I here? Yes, so the transformer has a built-in ratio of about times 16.5. And I found if I put 240 volts on the primary, it created a problem for too much voltage on the output here, too much high voltage. So to solve that problem, I've installed 2 variacs that I can use to reduce the primary voltage when I turn it on. And this has worked very, very well. Probably a little overkill on the variacs. I put 2 kilowatt 120 volt variacs, so they're referenced to ground or to neutral. And what I wanted here was about 190 volts, and I have that exactly, and I can dial it up to whatever I need and adjust the output voltage. So it works really well. It's a good solution. And these things are cheap these days. So basic rundown here is we've got a panel mounted circuit breaker, which is the main on-off switch. It's 15 amps. And it goes through an EMI filter. There's 2 neon indicators to indicate that both parts of the supply voltage are on. I hear Autumn chewing away in the background because he doesn't like me talking to myself here. He does that. Yeah, so the I chose to use solid state contactors here, thyristor type contactors. So I have a pair to engage the high voltage when the tetrode boards signal that they need the high voltage. So they're basically a 12 volt signal, turns these on. And when they turn on, they feed through these inrush resistors, which starts a little charge up circuit here, which turns these on and shorts out the resistors after, I don't know, half a second or something, but it just takes the big bang out of the engagement when these capacitors on the high voltage side are charging up, and it protects the high voltage diodes. In actual fact, I probably could get by without it because I am using a choke input power supply. But never hurts to be safe about this. I'm gonna have to, Autumn, I'm gonna have to stop that. Yeah, you go chew that somewhere else, not outside. All right, or make your noise somewhere else. Good dog. Yeah, so that's the inrush side. I used the 2 capacitors that came with the unit for the primary capacitance here on the full wave rectifier. They're nice poly-filled high voltage instrument type capacitors, really beauties. So I put the 2 of them in parallel, gives me 12 microfarad here. Then I'm using one of the 2 available chokes. There's 2 high voltage chokes in this thing originally, so they're big, heady, high voltage. I only need 1, so I got 1 in there. And then I've added a output capacitor here, 20 microfarad, and a bleeder. And I've got the usual safety resistor on the output to take shocks. And there's a high voltage bleeder for the meter. And to get a plate current meter, I've got a 10 ohm resistor to the ground. So that signal to the ground is the negative from the power supply going to the ground. and that provides a low voltage safety plate meter reading. So that's basically the power supply. I've got it, what I want is about 3,000 volts on the, stop again for a second. There we go. Don't have to stop. So what I've got is a what I was aiming for was around 3,000 volts at peak envelope power around 800 milliamps, something like that. And I think it's 2950 or something when I'm engaged on AM. Works fine. With no load, the plate there, the high voltage meter reads about 3,400 volts. But as soon as you turn it on, it drops to where you want it to be. So I'm quite happy with this. So that's that. So let's see. Let's go to the input. Oh no, wait now. I want to show you the bleeder, the high voltage bleeder. So this is the actual bleeder I made. It bolts on the output capacitor and on the terminals. So these are nice hollow ceramic wire wounds, so they cool off pretty well. So I've got 600K here and nice standoff turret type terminals and a piece of G10 to mount it on. So that's what's in there now. It works really well. It's good and stable and solid. So that's all good. Now I was going to talk about the input. So originally I had this set up here, which is a step-up transformer and a dummy load. I had some trouble getting this to have low SWR on the upper bands. It was okay on 160 and 80, and it crept up a little bit on 40, and wasn't really good at all on 20. I mean, it was workable, but I wasn't really happy with it. And in a bit of research, I ran across a German ham who had done a bunch of work on this problem, and he suggested using a sort of an input filter arrangement so he could do direct drive. And here it is here. I'm much happier with this. This works really well. So what we have is two -6 toroids here with 5 turns on each to build basically a little bandpass filter on the input. It has 3 points on it, a center tap which feeds the tube, and then one side goes to your dummy load, your swamping resistor, and the other side is your input. And the third resistor or capacitor that's missing here is the input grid capacitance on the tube. So they're all around 40 picofarads. So basically this thing is nicely balanced. But holy mackerel, does this ever work well. This thing is like flat as far as the exciter sees, all the way up to 30 megahertz. There's just no issues with it, and it drives the tube perfectly. I'm running my input around, my bias input points about -60 volts. I have absolutely no trouble driving this thing with exciter. I think 10 watts is kind of all you need to drive it. Maybe 12 if you really want to smoke this tube up to its upper end. But for AM use, I find I don't need much drive. So I'm driving this with a Johnson Viking 2, and its modulation isn't really great when you try to just turn down the grid current on it, the output sort of loading. So I run it through an attenuator, a -6 dB attenuator. So I run that Viking at about -60, or sorry, 30 watts, and it goes through a -6 dB attenuator, and it shows up here, and I've got just beautiful modulation on it. It's really, really well, works well. On this, so that's basically the circuit. These are the coupling capacitors. They're quite low impedance. You don't really need to worry about this on 80, but on 160 I found just one wasn't quite enough, so 2 of them in parallel. And this ham in Germany found the same thing. His website's worth looking at. DL2MDU has a really good website. He's built a couple of amps, including one with a 4CX1000A, which is how I found it. But his analysis of this input is really good, and I'm really happy with it. So much so, I'm going to change my 3-tube amp to match this as well. And I'm making parts for Roger's NCL2000 to match this. On the screen side, showed it on here. Basically, there's big bypass capacitors on the 3 screen taps on this tube socket. There's 2 varistors just to ensure that it's got lots of capacity. If there's a big voltage issue on the screen, it'll go right to ground through these varistors, MOVs. And I feed it through a small hinky looking little choke on a resistor, just to ensure that there can be no VHF oscillation sailing through this thing. It'll snuff it out. There's the bleeder resistor on the input, 30K, 10 watts. It's what's designed for this setup here. And that goes to your screen supply. I'm running around 350 volts. I think it's 345 right now. It's adjustable on the Tetra control board, but 345 seems to be just about right. And that's what's predicted in the iMac sheet. So minus 60 on the bias and plus 350 on the screen. Everybody's happy. So there you go, there's the power supply. Now, let's see what else I have here. I was going to show a couple of, well, yes, the location of the in the power supply. Here's a picture I forgot to show. So this is looking in from the front with the front cover off. So there's the output capacitor. There's the 2 right on the diode bridge. And this is a lashed up bleeder that I replaced with that one I showed you in the picture there. I mean, this would probably work all right, but I found these got kind of warm. They're not real accurate values for each. So one of them took a little too much current, and it was a little bit warm looking. So I decided to actually buy some good bleeder resistors and mounted them so that they're vertically to get a little better airflow. There is a little fan in this thing. It's at the back, blows air around, but don't have anything going directly on this. So anyways, it's replaced. It's all good. Everybody's happy. This is the safety resistor up here. This is the plate current to ground resistor. This is the bleeder divider for the kilovolt meter. And that's about all there is to see. This is the snubber on the 2 outputs of the Gates power transformer. And that, the back there, you can just see, that's actually the filament transformer. There was a spot in the chassis back there, so that's where it sits. It's out of the way of everything. And behind this little shelf bracket is where the diodes are in there. So you can service this thing from the front or back. It's easy to get at it if you take the covers off. And all the wiring is done with silicon high voltage wire. It's going to be rated for 15 kV or something like that. Does a really nice job. And I actually soldered ring lugs on everything so they can't come off, even if they get hot. So it's a good power supply. Not terribly compact or lightweight, but very reliable. So that's that. Now let's take a quick look at the transmit receive relays. Here they are here. A little bit fuzzy picture. These are 24 volt DC relays. So I parallel the contacts on both sides, and you need 2 of them to do this properly. So they provide the transmit receive function. They're not designed for hot switching. The G2 control board takes care of that because it controls these, but it ensures that the screen and the PTT are delayed until these close. So that prevents hot switching. Very nice feature of those boards. So you don't have to worry about the sequencing. This takes care of it for you. And another module worth looking at. This is my own version of the AM pickup monitor. Here it is here. This is for Steve's REA modulation monitor. This is the pickup for it. It has one lead that attaches to the pot, the output, and goes through this sampling power resistor here. And the output is rectified. Just standard pickup type gear. It's nothing complicated about it. So it produces a rectified, basically an audio sort of signal that goes off to the monitoring kit. That's a choke right there, by the way. Yeah, so that's that. All right, now let's see, is there anything else in here? I think I'm going to wind up this video right here. Oh, yeah, I got a couple of pictures. So this is the disassembly day when we were taking the amplifier apart at Derek's place. He was in the basement. There was no way we were carrying this thing up, so we were dismantling all the stuff, get it out of the basement. I think that's Gordon there, GVY, or GY, Gordon Young, VE1GY. That's me, and Roger EA1 RST is standing over there. And I think I got another picture of me taking things apart, showing my forming bald spot happening there. But as you see, we took everything out of this thing in order to get it out of the basement. And the last picture before I close this off. I do have one more here somewhere. Oh yes, Mr. Boredom there. Autumn. Everybody asks about Autumns. There he is. He's kind of bored. Not a very good picture. Fuzzy. Sorry about that. All right, so that's part 2.